this. Okay, we've got our acid derivatives, all shown kind of on the left, and what we identified was the thing that was different in each of them. So we were looking at the leaving group ability. All right, let's just pick the chloride and the carboxylate. If we look at our reactant energies, okay, what would we expect our reactant energies to be? Well, the nucleophile is all the same. We're really just evaluating a neutral structure, okay, to begin with. The bottom one isn't actually neutral, it's charged, but that one has increased resonance. So your reactant energies, let's see, do I have a nice picture? No, I don't have a nice picture. There's the nice picture. Your reactant energies will kind of shuttle around. Your intermediate is going to come in at roughly the same energy in all cases because it's the same nucleophile coming in and attacking. So what happens is that reactant, depending on the resonance stabilization or lack thereof, changes the energy of the reactants, which means the activation barrier to go from your reactant to your intermediate changes. Okay? And that's largely what's dictating the difference in reactivity between each of these. After that, your leaving group can leave, and we would see the reverse, or not the reverse, but the other end of this, where it's now transitioning down to how low in energy are each of those leaving groups. Okay? As long as you maintain that order, that's going to be the most important thing. Okay, so your acid chlorides are the most active and will react the fastest, followed by the acid anhydrides, esters and acids, which come in about the same, your amides and your carboxylates. Okay. That previous slide talked about rates of hydrolysis. Hydro for water, lysis, cutting. Okay? So we're talking about water coming in and cutting a bond. Which bond? We would kind of think the pi bond we're looking beginning to end. We're actually referencing the leaving group bond, the ability to kick out that leaving group or to see that bond end up breaking. Okay? Ultimately, the pi bond's the same thing, probably more accurate because that's actually what's breaking, but really we're evaluating that leaving group ability. Okay? So if we go through and look at these, the top ones hydrolyze very, very quickly, and the bottom ones not so much. Okay? And again, that goes to the individual reactivity of those starting materials. Okay? So stability of the leaving group, we already addressed. Okay? This is kind of a cheat because if you notice on our energy diagram here, do we actually have the leaving groups leaving? No, so we shouldn't really be using leaving group ability to rank the order of reactivity of these. Okay? The ranking of the leaving group ability is kind of a cheat because it gets us to the correct answer but for the wrong reason. Because the leaving group hasn't left yet, we can't really evaluate or use that as an evaluation for why we see different rates of reactions. Okay? The different rates have to come in with the electrophilicity of each of those species. Okay? And you could draw resonance or inductive arguments for each of those. At this stage, we're behind, so I'm going to say we can cheat. Okay? So really what you're looking at, okay, if the most stable thing is your leaving group, okay, then what happens? If your leaving group is more stable than your nucleophile, what happens? We get a reaction. Okay? The reaction should happen because we're saying the leaving group, this species, is favored over the nucleophile. Well, if the leaving group is favored, which side of the reaction is going to exist? Where's the leaving group? The leaving group is on the product side, so we would expect a reaction to occur. If the nucleophile is more stable than the leaving group, then what happens? Now the reactant side is favored in this. Okay? So it's ultimately kind of a hand-wavy argument is just the balance between those two, helping us to decide when a reaction should occur or not. Okay? Most of this kind of section on acid derivatives is how do we interconvert between them. Okay? And that's where things can get interesting. Can I go from the anhydride to the acyl chloride? What's changing? So ignore all the little fancy arrows and drawings out there. Would I expect to be able to go from the anhydride to the chloride.
Is it anhydride with or
Hence the arrows pointing up. So this is our reactant. This is our product. What do I need to cause that to happen?
Well, the leaving group in this case would be the I don't know how to say it, the ester.
I'll accept that. That would be this piece. Okay, so our leaving group would be that. It's not an ester, this would be our carboxylate. Okay, what would the nucleophile be? Okay, the nucleophile would be, that's a Cl, would be our chloride. Which is more stable? Okay, why is the chloride more stable?
It's bigger.
It's larger than the carboxylate. Because it is larger, that makes it more stable. Would I expect to be able to go from reactant to product? No. Okay, so the anhydride to the acyl chloride doesn't happen.
Unless you want more
Okay.
reactive.
How could I possibly get to the acid chloride then? Well, never mind, ignore that statement. So ignore that statement. How about going from the acyl chloride to the anhydride? Now what changes? Now I'm saying reactant to product. What's the leaving group?
Chloride.
The chloride is now the leaving group. And what is the nucleophile? The other species, right? Would I expect this reaction to occur?
Yes.
Okay. The chloride is much more stable. That is now a very swift, easy reaction. Okay. So what we're looking at is kind of a trend in the energies. Once we're at the acyl chloride, we can go down very quickly. Not so hard to climb back up, or not so easy to climb back up. Okay. So once we're lower on our tree, we can't move upwards easily. If we can't move upwards easily, what are we going to need? Very specific reagents. Okay? Because the acyl chloride is the most useful, why would it be the most useful? What could the acyl chloride become? An anhydride, an ester, the amide, even the acid. Oops, I left the acid off. The acyl chloride can become anything. What can the anhydride become? Everything except the acyl chloride. What can the amide become? Just the carboxylate. Okay, we can only transition downwards. But if the acyl chloride is so cool and useful and important, what happens if I use it all? If I can only go downwards, what happens to being able to use it anymore? I wouldn't be able to make it again. I would need a special reagent to put that chloride on there because it doesn't want to go on easily. I would have to use a reagent that is insanely high in energy to force that transfer.
What if you want to go from the carboxylate, which is all the way at the very end, to the anhydride?
Can I go from the carboxylate to the anhydride?
I mean, according to our definition, no, but
No.
but we have the same little ion thing that's going on.
Just because the ion is present doesn't mean I can explicitly do it. That's what all of these arrows are on our chart. These arrows are supposed to help us see how we could transition between them. To go from the carboxylate to the anhydride, what do you have to do? Okay, well, that red arrow is my goal. I could add an acid. If I add an acid, what do I become? A carboxylic acid. Now what can I do once I have the carboxylic acid? I could use thionyl chloride to make an acyl chloride. Once I have the acyl chloride, what can I do? I can react the initial starting species to make the anhydride. So we can transition upward, but we have to transition upward through very particular steps. The arrows are intentionally included in here. Some of them are reversible, some of them are not. You have to be aware of how we move through. We cannot move directly from, or in purple/red, we can't make that single jump. we have to move through each of the intermediate stages. Okay? Questions about that? Okay? Most of the rest of the chapters are now divided up into kind of pseudo sections, or most of the slides, saying, okay, we take hydride, a hydride source. Where do we get a hydride source? Sodium hydride, Touche does give you a hydride source. Why would that not be as relevant for these? All of these are highly electrophilic. We're looking at that electrophilic addition. So a hydride source isn't going to be useful if it's sodium hydride, because sodium hydride acts only as a base. I would need sodium borohydride or lithium aluminum hydride. Those could then do nucleophilic attack. If they did nucleophilic attack on an acyl chloride, what would happen? Because we're all super excited about nucleophilic additions. We're talking about H minus, right? Where would the H minus attack? The carbonyl carbon, which would do what? Break the pi bond, and we would show an intermediate. We would show the tetrahedral intermediate. What happens in that tetrahedral intermediate? The electrons come back down and kick out the chloride. What would you end with? An aldehyde. Does sodium borohydride react with aldehydes? Does sodium borohydride react with aldehydes? No?
It has nothing to take out.
Okay. So let's take a minute, let's pause, because why not? Let's see, I wonder if we talked about that at some point in the past. Say we open up our slides here. Lectures. Let's close that for a moment. We get an idea here. So lectures, Unit 2, nucleophilic addition. Of course, it's going to open up on the other screen, because why not? And we could look at all those stuff. Enolates, yeah, enolates, those weren't exciting. Carbonyl chemistry. Ooh, a spider diagram. Oh, hydrides, where they were nucleophiles. What could sodium borohydride react with? Electrophiles, or carbonyl compounds. Is an aldehyde an electrophile? Yes. Does it have a carbonyl? Yes. What does that mean? It reacts again. Right? So what we have to do is remember all of those old reagents and the context behind those reagents and how they would apply forward. Virtually everything in this new unit is a repeat of the previous unit. Because when we react hydride nucleophiles with these species, we end up forming aldehydes or ketones. Right? Sorry, I said hydrides. We'd be forming aldehydes. We have to remember that aldehydes will continue to react. Why will aldehydes continue to react with nucleophiles? They are still electrophiles. So they will react again with the acyl chloride. So we have to know something about those reactivities and apply them both to the new material and backwards to the old material. So what you may see in a textbook or in a discussion of these reagents online is that if I take an acyl chloride and I react it with sodium borohydride, what do we typically see as the answer? And now we go, oh my God, it's a whole new reaction. Nothing about that reaction is new. Right? You know all of that chemistry. We've been talking about the how and the why. Okay? That's the point of reviewing that chemistry and holding it. If you aren't holding it, you have a new reaction to memorize. Okay? Hold on to the hows and whys of these things, and you have less work to do. If you aren't trying to figure out the how and the why, you're going to have more and more and more work. Everything becomes a new topic. Okay? That can be insanely stressful. Okay? So, in this, you might say, well, everything moves downwards. To get upwards, we have to move through special chemistries. Ultimately, the special chemistry that we have to move through, pretty much always thionyl chloride. If I want to make any one of these, I need to get to the acid state. Okay, or sorry, the acyl chloride state. I have to get there. The only way to get there is through thionyl chloride. So thionyl chloride as a synthetic reagent is going to constantly show up because it puts me at the top of the food chain. I can now move down through that food chain very quickly and easily. Right? As with all things, we might say, well, if we always do that, then it's really straightforward. Could we end up with exceptions? What happened here? What did we start with? An amide. What did we end with? A carboxylic acid. If we go back to our list, there's the amide, there's our carboxylic acid. Isn't the acid higher on the list? Okay. We can't go from a low rung to a high rung, but what is this arrow showing? It's saying that I can. Why is that one step allowed but none of the others? Is this some weird exception? Right? If you want to just memorize the results, yes, it's now a weird exception for you to memorize. Or if we consider how the reaction works. Okay? Because this reaction is not actually going to the carboxylic acid, it's going to the carboxylate. The amide is actually going lower than it. Okay? Once I form this, what can I do? I can add acid to very quickly make the acid. So when we look at the overall reaction, we might think that this is counter to what should happen. That shouldn't happen. It shouldn't go up. The reason it's going up is because the amide isn't going directly to the acid. It's going to the lower rung. We're then following it up with a second step. What is that second step doing? Taking us the rest of the way.
But if it, so how does that, I don't know if this, that was just like trying the mechanism of that, I don't know if it's complicated, but if you do have just like OH attack, is that Pyridian?
What is the OH
Is that just
attack?
The carbonyl?
So- Okay, so when you're looking at that, you just said OH. Why did you ignore the potassium? Isn't there a potassium there?
Yeah, just to balance the charge.
Potassium there is to balance the charge. So we've got a negative, reconnect please. We have a negative hydroxide. Where's that negative going to attack?
Carbonyl, the most positive thing.
The most positive thing, the carbonyl, which is going to then cause what? The pi bond to break. Okay, what would the result be? I'm not drawing out that awful ring. Whoops. And then unfortunately I do have to draw this awful thing. Okay. Now what could happen?
Those electrons could come down and kick off.
Cook out.
Yeah.
Maybe after grades. Okay. Reforming that, we'd end up with the OH, and what else would we have? N minus. Is N minus a stable thing? No. Because it is unstable, what is it going to do? Okay, it's going to find a positive. Where's there a positive? Immediately in that carbonyl, it could immediately go back. The problem with this step, it is heavily equilibrium dependent, and it's going to favor the reactants. Why would we favor the reactants over the nitrogen?
Negative nitrogen is worse.
Where's the charge in that step before?
Negative oxygen.
Negative oxygen. Which is more stable, a negative oxygen or a negative nitrogen? The negative oxygen, because it's more electronegative. That equilibrium heavily favors the reactants. Okay? So we would expect very little progressing forward to this acid state. Is there another positive thing floating around? H plus. Where's that H plus? Aren't we under basic conditions?
Then we put it in second step.
Nope, we aren't even in the second step yet. Not in oxygen. What is this functional group right here? Which I'm now overlaying in orange over red, which was a horrible decision, but that's a carboxylic acid.
So that's why.
The nitrogen can immediately pick up that hydrogen, shuttling the electrons to the oxygen. What's the result?
Then you have
A carboxylate, the negative charge, and we'd have our happy neutral nitrogen. Which is more stable, a negative oxygen or a negative nitrogen? Negative oxygen, by a lot or a little? Well, a lot. If we compare purple to orange, we're now going to get a very small reaction, okay, going backwards, right? So most of that's progressing forward. There's another thing that's saying that that orange or that red arrow that I just drew in should actually be non-existent. Why should it be non-existent? It's no longer there.
all these red and orange guys are killing me.
That collection of red arrows?
I can't tell if it's purple now.
Shut up.
Is non-existent.
Why should it be non-existent?
Because you're in basic conditions and you form an acid?
Nope. This step was reversible, negative oxygen, negative nitrogen. Why is this step not reversible? Why not? That's still saying that, because if you're making that argument, then the red arrow here should never have happened. And if that never happens, can I get the orange product? No. And if we just evaluate nucleophile and leaving group, we're comparing a negative nitrogen to a negative oxygen. Negative oxygen is more stable. This shouldn't happen. Why is that orange arrow singular direction to the right? No.
Electron geometry.
What is special about that negative oxygen? Oh. There is a resonance stabilization on that oxygen. So not only is it a more electronegative oxygen, it has a secondary resonance effect that drops its energy even further, meaning that that orange reaction is massively irreversible. Because of that step under these conditions, step one occurs. All because of that last step. We've never seen anything like that before. Yes, we have. The aldol condensation happens for that same reason. Okay? There is a massive stabilizing effect that allows for that to occur. Okay? We have to be cognizant of that stabilization effect. That's why it's happening. Okay? The other reactions don't have that ability, so they can't occur. Okay? Now that we've formed or stalled out our reaction, now what happens? I can now move on to step 2 and add an acid. Why would the acid protonate? Didn't I just say that is completely irreversible? It is completely irreversible under basic conditions. As soon as I shift to now acidic conditions, it fully reverses. Okay? So looking at the acid-base equilibria is one of the things that helps us contribute for why we move certain directions when we move through a reaction. We have to be thinking about those pieces, or we memorize all of those reagents. Those are your two options. If you want to memorize, that is fine. That is your call. I have no problems with that. Okay? Except I can't help you do that. Okay? So if we look at a free energy diagram, the first step is going to require a significant amount of energy. Why are we going to go up in energy to our intermediate? Right? We're adding charge. Why is the next step, I still have charge, why is that next step lower in energy? Where's the charge located? Nitrogen versus oxygen. Whoops, sorry. We get a resonance stabilization. Sorry, I pointed to the wrong thing. The resonance stabilization helps to stabilize and drop the energy. We don't get a significant or a huge significant drop because nitrogen doesn't want to hold the charge as well as the oxygen. But that resonance within our carboxylic acid helps to stabilize. Then what happens? Well, can nitrogen stabilize that negative very well? Nope, so what does it do? It grabs a hydrogen from the most acidic source, which is immediately next to it because it just came from that structure. That step is now massively irreversible, okay, due to the resonance stabilization of the carboxylate salt. Okay? That's what drives the reaction forward. Okay? So, in and of itself, that reaction is actually kind of boring and not all that exciting. So we actually want to make it a little bit more exciting. We switch to a named reaction. Okay, everybody's favorite. Okay, we've got the Gabriel reaction. We start with phthalimide. Okay, and we add KOH. What is KOH going to do? It's phthalimide.
Sorry?
It is phthalimide.
PH silent.
pH is silent.
Sound.
What does the KOH do? Okay, that is solely there to remove the hydrogen from the nitrogen. Okay, what would that then produce? Let's see, do I show the next part? What would we get if we removed that?
Why isn't this active carbonyl negative? Out of curiosity.
We'll get to that in a second. We would get a negative nitrogen. And what is special about a negative nitrogen? Stupidly strong. We could run it as a base. It's also nucleophile. Okay? And so the nucleophile characteristic is going to stand out. Okay? It's going to become a better nucleophile than other systems because the substituents around it are now actually held back away from it because of the cyclic structure. Okay? To Colin's point, why did the hydroxide not attack the carbonyls?
Is it because it's there?
Is that H more reactive? It's more positive than the electrophilic carbon?
So that hydrogen is going to be a little bit acidic, which can help us out. Okay, why would it be acidic?
Resonance to stabilize the charge.
Resonance becomes a little bit of a borderline issue because there was already resonance in there. Why would that hydrogen become acidic? If resonance isn't your answer,
Nitrogen's really not pulling on it.
so the nitrogen is not as electronegative as oxygen, so we might expect that a negative nitrogen would be less stable than the negative oxygen. What is extra special about this? There was a suggestion for resonance. There's an argument that the resonance is already occupied. It's not resonance. Induction. What do we have here? 2 electronegative oxygens. It's the 2 electronegative oxygens that are helping to make that nitrogen or that hydrogen acidic. Okay? That increases the acidity of the hydrogen enough that what does it overcome?
The positive carbonyl.
Yeah. And so our hydrogen becomes the primary reactor instead of the hydroxide attacking the electrophilic carbons. Okay? So then what happens? You have a negative nitrogen. What could that negative nitrogen do? Okay? It should react to something that's missing electrons, something positive. That could be a hydrogen. That's pretty boring. That takes us backwards. What do they add instead? An alkyl halide. Why are alkyl halides interesting? They are electrophiles. What happens? And we would now get a substitution. Okay, some of you might be saying, well, that's silly. Couldn't I have just done that with a normal nitrogen? It's a good question that you asked me, but since I asked it first, you get to answer it. Could I have done that with just a normal nitrogen? Couldn't I have just done NH3 and reacted that with Br?
Did you say there were inductive effects? So those would be like pulling the lone pair and the nitrogen inward, so we don't want to go out and grab something.
Right. There are inductive effects that help stabilize this. The electrophilic carbon is positive enough that it allows that to happen. Okay.
Don't you need that negative charge though?
Do I need the negative charge for the nitrogen to be a nucleophile? No.
For the alkyl halide?
It does not need to be negative. The alkyl halide's electrophilic enough that the nitrogen, whether it's negative or neutral, will attack it.
Because you would have broken the octet.
Nope, it doesn't break the octet down here at the bottom either. So all I did was attach a nitrogen to a carbon, right? Both cases.
If you did 9, do it again.
Now I can do it again.
Yeah, nitrogen attacks again.
I thought you
It's not that it can do it again, it's that
can do it again because of those.
it will do it again for this one. When we're looking at the free amine reacting with our alkyl halide, what is the problem with that reaction? The nitrogen is still a nucleophile, which means it will continue to react with the alkyl halide. The free amine in the alkyl halide produces how many products? Less than 5. 4 products. Primary, secondary, tertiary, quaternary amines. Okay? We're getting a mixture of products. That sucks as a reaction. How many possible products can I get in this top one? Couldn't that nitrogen now come out and attack another alkyl halide? Doesn't it still have electrons, just like the bottom one?
Just 2, but then it's positive. Right?
Okay, just 2, but this one would have formed the quaternary that was positive. Why is this one not adding another carbon group?
Oh, because now you destroyed resonance.
What is that lone pair doing in the case of our Gabriel synthesis? Stability through resonance. That lone pair is not accessible for nucleophilic attack. Right? Which means when we run the Gabriel synthesis, I only have one lone pair on the nitrogen that is nucleophilic. When I run the standard amine reaction, every time I run the reaction, I generate a new lone pair that can react again, which is why in the bottom case I get the primary, secondary, tertiary, and quaternary amines. It stops at the quaternary. Why would it stop? There's literally no more lone pairs. Why does the Gabriel synthesis stop? The lone pairs are occupied by resonance. It is that resonance occupation that prevents it from continuing to react. So we did all of that to make a single nitrogen-carbon bond. You might then make the argument as well, okay, fine, let's just say I just accept a 57% yield and I end up with the primary amine, the bottom case, right? Do I have a primary amine with the Gabriel synthesis? That nitrogen's connected to 1, 2, 3 carbons. Do I have a primary amine? No, Mike, you say, the whole point of this was to end up with a primary amine and you aren't making one. That's really dumb. What's step 3? Step 3, we add hydroxide. Didn't we already add hydroxide? We added it initially, and what did it react with? The hydrogen. Why did it react with the hydrogen? Why was the hydrogen acidic?
Because of the
An inductive effect. Do I have a hydrogen anymore? No. Where can that negative hydroxide attack? What positive? It can attack the carbonyl.
Wait, hold on. No, not that one, the top one.
If it attacks the top one, look at the arrows that are already on there. Once the nitrogen has done resonance, it's stabilizing that carbonyl. It's not susceptible to attack anymore. But what happened to the other carbonyl? Now there's nothing to stabilize it. The hydroxide can come in and attack that carbonyl.
So the chemistry is happening in all 3 different areas?
Through the course of this reaction, I get chemistry happening at the nitrogen and at both carbonyls. You are absolutely correct. All right? At each individual stage, chemistry is only happening at one position. The chemistry with those purple arrows on that far side, I would argue that's not chemistry. What is that? That's resonance stabilization. That's not chemistry. There's no bonds really being broken or made. Remember, pi bonds are just resonance. Right? So we're saying that that stuff is just saying it's not active, which means the carbonyl is left over. The only thing that's happening is hydroxide attacks. Hydroxide attacks it just like it did in the previous sequence of reactions. And what do we end up forming? Tetrahedral intermediate followed by breaking. The electrons come back down, kick out the nitrogen. Then what happens? We'd have that negative nitrogen. The negative nitrogen deprotonates the hydrogen. We'd have NH. This would now be negatively charged. So that one that was a tertiary is now a secondary. But what functional group do I have? I have an amide. And can amides react with hydroxide? Yep. It can react a second time. In that second approach, it attacks, breaks the pi bond reforms, we kick out the leaving group, the nitrogen picks up the hydrogen, and after all of that work, I have a primary amine. Okay. The whole point of the phthalimide structure is to make a primary amine. What happened to the rest of the structure? It's still there. Do I care about it? No, because my goal was to make a primary amine. Are primary amines easy to make? No. Ta-da! That's why the name is attached. Okay, what is the remaining structure that did not get counted as important? It is the dicarboxylate salt. With that, we will go ahead and end, and we will pick up on Wednesday. I will hopefully